Volkswagen was the first car to have some kind of communication, and this was way back in 1968. Ever since then, communication and diagnostic systems have evolved from the crude OBD1 systems to the more intelligent and upgraded OBD2 systems. Mulungi Steven is my name, and I'm the head technician at Nana Auto Diagnostics, and today I'll be beginning a 7-part series where we shall be talking about the different communication protocols, or you can call them languages, that are used in vehicle communication systems. Just like the human body uses the endocrine system and the nervous system to relay information from one part of the body to another, there is also a system in vehicles that is used to transmit data from one point to another, and that system is what we know as a communication network system. And that system employs a number of different protocols, or you can call them languages. And today we shall begin our discussion with the J1850 protocol. These protocols were standardized by mainly two organizations, and that is the Society of Automotive Engineers, abbreviated as SAE, and the International Organization for Standardization, abbreviated as ISO. So let's first look at these protocols, and there are 7 of them, and each will be covered in a separate video. So that constitutes the 7-part series that I'm talking about. These protocols or languages include the SAE J1850. Now, this comes in 2 flavors, which is J1850 VPW, which is variable pulse width, and J1850 PWM, which stands for pulse width modulation. Then we have another one, which is ISO 9141-2, and this defines the K-line protocol and usually uses an L line, and this is optional. We shall look at that in detail when the time comes. And this protocol was upgraded to ISO 14230-4, which is KWP2000, standing for Keyword Protocol 2000. And next we shall look at the ISO 17987, which defines the LIN, which is Local Interconnect Network, and also move to ISO 15765-4, which defines the Controller Area Network, or what we know as CAN network standard. Next, we shall also look at the ISO 17458, which is a standard for FlexRay, and move on to ISO 21111 standard, which is a standard for automotive Ethernet. And we shall also look at the ISO 21806 standard, which is for MOST, standing for Media Oriented Systems Transport. If you have not yet watched my previous videos, I would recommend you first watch them. One talks about the history of OBD, which is onboard diagnostics, and the other talks about the different terminologies that are used in automotive communication systems. So those 2 videos, they lay a foundation on what we are going to be talking about today and in the future videos. It is also important to note that not all these protocols can be accessed on the OBD2 port. Now these are the protocols which can be accessed and tested on the OBD2 port, and they include the J1850 VPW, the J1850 PWM, the K-line protocol, or the upgraded version, which is KWP 2000, standing for Keyword Protocol 2000, and lastly the CAN, which is the Controller Area Network. So those are the only communication protocols which can be accessed on the OBD2 port. The rest of these protocols, which include LIN, which is Local Interconnect Network, FlexRay, MOST, which stands for Media Oriented Systems Transport, and Automotive Ethernet, cannot be accessed on the OBD2 port because these protocols are mainly used for module-to-module communication. So before you start diagnosing any vehicle, you ought to understand where to begin your diagnosis or testing, how to test, and what to expect as a known good or bad, as this will save you tons of your time and increase your efficiency as a technician. And that's what exactly these series are designed to do. We shall cover all the communication networks, and we shall know how to test them, where to test them, and what to expect. And when we move on to our practical session, where we shall look at these networks and their behaviors by using the scope, we shall be able to appreciate these concepts, because we shall cover a number of conditions and subject these networks to a number of faults, such as open circuits, short to ground, short to power, short to each other, and we shall be able to appreciate these concepts more. Let's begin our discussion with the SAE J1850, which is a standardized and serial communication protocol that allows several ECUs, which refer to electronic control units, to communicate with each other, and also allows these ECUs to communicate with a scan tool when plugged in the OBD2 port. This protocol was developed and adopted by the Society of Automotive Engineers, abbreviated as SAE, in 1994, and it came in two flavors, the VPW, standing for Variable Pulse Width, and PWM, standing for Pulse Width Modulation. Now the VPW was adopted by the GM Group, which is General Motors Group, and the PWM was adopted by the Ford Group. So these two protocols will be found in mainly US-based cars in a production date ranging from 1996 through 2007. So where does the J1850 sit in the protocol world? So J1850 is considered as a medium speed communication protocol. So let's see how these protocols are categorized. These protocols are categorized in three classes, which include Class A, Class B, and Class C. Now, Class A is considered as a low-speed class and is used for simple body functions such as seat memory and mirrors. Class B is considered as a medium speed class, which is usually used for diagnostics, emissions control, and engine data. And it is within that class where the J1850 lives. We also have Class C, which is a high-speed communication network, and this is usually used in safety-critical systems such as the ABS, which is the anti-lock braking system, and airbags. So every time you come across a network having a letter A, B, or C in front of its name, that is an indication of a class where that network lies. For instance, this is usually used in CAN, which is Control Area Network, where you find the big CAN and the C CAN. So every time you encounter the big CAN, just know that is a medium speed CAN network. And every time you encounter a C CAN, that should be an indication to you that they are talking about a high-speed CAN network. Now we shall look at these in detail when we are talking about the CAN network. So as we can see, the SAE J1850 protocol is not that slow or fast. It is just in the right spot where it was designed to be. Now that we have seen how the J1850 fits into the protocol world, let's see how it fits in the OBD2 world. When you plug a scan tool into the OBD2 port, the scan tool will start communicating with the electronic control units, or you can call them the ECUs. The data that is flowing back from the ECUs will contain everything that your vehicle is doing in real time. And this includes the following: the engine RPM and vehicle speed. Now this is monitored continuously, so your ECU knows exactly how hard the engine is working and how fast the vehicle is moving at any given second. 2. The coolant temperature and oxygen sensor readings. Now these are critical for emissions, compliance, and fuel efficiency. And it also gives a feedback of the active and pending diagnostic trouble codes, or what we know as DTCs. As I have told you earlier, the J1850 comes in two variants, which is the VPW and the PWM. The VPW was adopted by the GM group, and the PW was adopted by the Ford group. And these are US-based car manufacturers. So let's go ahead and explain each in detail, and we shall begin with the J1850 VPW, which is variable pulse width, and we shall explain both basing on these parameters, which include the physical layer, the pin allocation on OBD2 port, the modulation method, the speed or data rate, the topology that is employed in each, and the voltage levels. So for the physical layer, the VPW uses a single wire, and this is allocated to pin 2 on the OBD2 port. And I have covered the OBD2 port in detail in one of my previous videos. I've tagged the link in the description below, where I talked about the history of the OBD and the OBD2 pinout. So if you want to know more, you can go and watch that video. For the modulation method, this protocol uses the VPW, as the name suggests, where each bit represents either a 0 or a 1, depending on the variable duration of the pulse. Now let me explain that in detail. So let me explain how modulation is attained when it comes to SAE J1850 VPW. As the name suggests, it's a variable pulse width. So what happens is, whenever the bus is at idle, it rests at 0 volts. So in this case, we don't have any communication on the bus. So when you connect your scan tool and attempt to communicate with ECUs, or it may even be an ECU communicating with another ECU, it will drive the bus voltage from 0 to 7 volts. So at this point, we can say that the bus is active, and it will stay active depending on the data that we are transmitting. For instance, if the ECU is transmitting a 1 0 0 1 1 binary code, we realize that it is going to stay active when it is transmitting the 1. So it will stay active for that duration of time, and when it transmits a 0, the voltage is going to drop to 0 and stay at 0 volts for this time frame, and still go up when transmitting a 1, and it will stay active again when it's transmitting a 1. So in this case, we are adjusting the width of the pulse as we are transmitting the data. So in this case, when you are transmitting a 1, that is the pulse width. If you are transmitting 2 1s, so to say, the pulse width will be twice as compared to the 1 where we are transmitting a 1. Someone out there may be asking, how does the computer or the ECU know that this is a 1 or a 0? Now that is determined by the program that is written within the ECU, and usually any voltage that is below 3.5 volts, it is considered as a 0, and any voltage above 3.5 volts is considered as a 1. So the bus will be in the passive state whenever the voltage levels go below 3.5, and whenever the bus voltages go above 3.5 volts, then it will be in the active state. Let me also share briefly about the common faults that we may encounter with this communication protocol. So whenever you have this wire, remember it's a single wire, if it is shorted to battery voltage, it means we shall not have this square wave. Instead, we are going to have a single line indicating battery voltage. So we may have 12 volts, but if the voltage is higher than 12, it means you're going to record battery voltage here. So we shall be able to look and explore those various faults on the network. So keep yourself in the channel. The speed or data rate is about 10.4 kilobits per second, and the topology employed in this system is a masterless architecture. Now, in this system, every node can transmit data as long as it senses the bus is idle. And next, let's look at the voltage levels. Now, the voltage will swing between a 0 and a 7. Let's move on to the J1850 PWM, which is pulse width modulation. And for the physical layer, this utilizes two wires, the bus positive and the bus negative. And the bus positive is allocated to pin number 2 on the OBD2 port, and the bus negative is allocated to pin number 10 on the OBD2 port. And just as the name suggests, the method of modulation is pulse width modulation. Let me explain that in detail. Let me talk about the SAE J1850 PWM communication protocol. Now, this communication protocol uses two wires, unlike the VPW, which is the variable pulse width, which uses a single wire. And this protocol uses a fixed frequency in order to transmit data on the bus. So let me create two time intervals, which is this one and this one over here. And remember, we said that this communication protocol uses two wires. So on one wire, we're going to have five volts, and on the other, we shall have 0 volts. So what happens is, whenever a module initiates communication on the bus, or whenever you connect your scan tool on the OBD2 port and attempt to communicate with any ECU or module, it is going to drive the bus from the passive state to the active state. And what happens is, the 5 volts is going to be pulled down, and the 0 volts going to be pulled up. Now, the duration this pulse will stay active will determine whether you're transmitting a 1 or a 0. For instance, if you're transmitting a 1, this pulse will stay active for a period of 64 microseconds, and then it will drop to 0 volts for a period of 128 microseconds. Likewise, this voltage will also stay dormant for 64 microseconds and also rise for a period of 128 microseconds. So it has stayed dormant for the same time as this one, which is 64 microseconds. So in this case, we are transmitting a logic 1. Now, whenever we are transmitting a logic 0 on the bus, what happens is, we are going to drive this voltage here from 0 to 5 volts. But this time, it will not stay active for 64 microseconds. Rather, it will stay active for 128 microseconds and then drop to 0 volts and stay there for a period of 64 microseconds. Likewise, its counterpart will drop to 0 volts and stay there for the same time period and also rise for the same time period, which is 64 microseconds. So these two mirror each other. So in summary, whenever we want to transmit a logic 1 on the network, which is this one here, we need to drive the bus voltage from 0 volts to 5 volts for this time period, which is 64 microseconds, and then lower that voltage to 0 volts for a time period of 128 microseconds. Likewise, the 5 volts is dropped to nearly 0 volts for the same time period and driven up to 5 volts for the same time period. And if you wish to transmit a 0 on the bus, we drive the same voltage, which is 0 volts, from 0 to 5 volts for a period of 128 microseconds, and then drop that voltage, and its counterpart is also dropped from 5 volts to 0 volts for 128 microseconds. So you see they move in the same time interval. So what is that picture that you look at and see if you're transmitting a 1 or a 0? So you look at the 0 volt and see how it is behaving when it is active. Whenever you realize that this pulse here is shorter than its corresponding pulse in the next data stream, then that should be an indication that it is transmitting a 1. If this pulse is longer, then it is transmitting a 0. We also talked about this protocol utilizing a fixed frequency system. So you realize, by definition, frequency is the number of complete cycles made per second. And remember, we began this by splitting it into 2 time intervals. So we had this and also that. So realize here, the time difference is the same, 192 microseconds. And also here is the same, 192 microseconds. So you realize the frequency at which this communication is happening, it is the same. That's why it is called fixed frequency. Now, this protocol operates at a speed or data rate of about 41.6 kilobits per second. So we can see it operates at a higher speed than the VPW, and it uses the same topology as the VPW, which is a masterless architecture. And in this, any node can transmit data as long as it senses the bus is idle. And the voltage levels will swing between 0 and 5 volts. So let's compare these two protocols side by side, and we shall begin with the pinout on the OBD2 port. So we realize that the VPW is only allocated to pin number 2, which is the bus plus, and it only uses a single wire. And for the PWM, it uses 2 pins, which is pin 2 for bus positive and pin 10 for bus negative. So if you are diagnosing any car and you're not sure about which protocol is employed, you can just look at the OBD2 port and focus on pin number 2 and pin number 10. If you have pin 2 present and pin 10 absent, that should give you an indication that you are dealing with VPW. If you have both pins present, that is pin 2 and pin number 10, that should be an indication that you're dealing with PWM. Why are we going through all this? You realize that when you are dealing with the VPW or the PWM, you will use different testing methods and you will have to expect different results. For instance, when you are dealing with the VPW, you expect your voltages to range between 0 and 7, and you only have a single wire. When you are looking at PWM, your voltages will range from 0 volts to 5 volts, and you'll be having 2 wires on that network. So understanding these networks is very important because it will save you a lot of time, because you know where to test, how to test, and what to expect. And another thing that I would like to point out, if you're dealing with Ford cars, now Ford shifted from PWM to K-line. That was 2005, 2007, before the CAN protocol was mandatory in 2007. So if you're working with Ford cars between 2005 through 2007, you need to verify with your wiring diagrams to see what exactly you're dealing with, because you may have some models using PWM and others using K-line. In the next video, I'll be covering the K-line communication protocol, which also includes the L-line and its upgraded version, which is known as KWP 2000, standing for Keyword Protocol 2000. Thank you for watching and see you in the next video.